I'm the PI on a PRAC grant, so that's why I'm here. Thanks for sticking around and listening. So you might ask, what is OpenAtom and why are there so many damn people on this talk, right? That's the website for this OpenAtom. It's a piece of software. The reason there's so many people listed here is because, well, who pays all these people, right? That's a good question. So we have a three-way grant. Myself, Sanjay Kala at UIUC, and Glenn Martin at IBM to develop software and do some applications. So we're funded by the NSF via this grant. It's a Software Institute grant. And the software package we're developing is called OpenAtom. It does density functional theory, which is a way of thinking about what electrons do in the ground state. And we've added GW, which is for electronic excitations. It's based on plane waves, which means Fourier basis representation for electrons, so it's general. And pseudopotentials, so we only deal with the chemically active electrons. And we use this charm++ parallel infrastructure developed in Sanjay Kala's lab. Okay? So it's a computer scientist, a physicist/chemist, and a physicist/material scientist all working together. Okay, what is this thing and what does it do? So it's a massively parallel ab initio code that does molecular dynamics. And it also now does electronically excited states using these Green's function methods. This is not a talk about methods. So maybe some of this means something to you and maybe it doesn't, but apologies. Okay, so we're going to describe the electrons in the material quantum mechanically. Okay, so it's not effectively, we explicitly describe them directly. And we use basic physics, like charges attract and repel, electrons have kinetic energy, things like that. So no fudge parameters or fits. Fourier basis, that's the plane waves, is very general. And we're using a high-performance charm-based FFT library. If you're an expert, we use LDA or GGA, depending on what we're doing. Standard stuff. Carr-Parnell or Born-Oppenheimer molecular dynamics for the ground state. And the GW approximation is used for the electronic excitations. Okay, so that was what's what to OpenAtom. We're going to be studying metal organic frameworks. I'll tell you a little bit what is that, what we've learned so far, and then a little bit on making our GW run faster on OpenAtom. All right, so hydrogen, that is the gas, H2, is a candidate for green energy because it's energy dense, it burns cleanly into water, but it is hard to store it because it's a gas. So a lot of effort has gone into thinking about this. This is the DOE's kind of a roadmap for that. There's physics-based methods, so you squeeze it or compress it or liquefy it. Then there's materials-based, so you store it in a material, lots of different materials. One of them is called a metal organic framework. Okay. So these are porous materials. I'll show you a picture. They have a lot of interior surface area, so you could store plenty of hydrogen. They're complicated materials. The details are not very well known. And to date, the H2 storage is not very good. So part of the question is why? Can it be improved? Yes or no? That's the basic science question. So a typical MOF looks like this. The yellow ball is to represent empty space. Okay? So basically, there's a bunch of things on the corners here, which are transition metals surrounded by oxygen, and then there's little organic linkers, like a benzene type of thing, linking the two corners. So it's a lot of open space, and that's where the hydrogen is going to go in there and move about and stick to the walls. The hydrogen tends to like to stick to the metals, which in this case is zinc. All right, so here's the official one we're studying. It's this wonderful chemical name. It's got 424 atoms in the simulation cells, and the idea is to change zincs to other metals and see if things change. Okay, how does the hydrogen bind and diffuse inside, and what's the temperature and loading dependence? These are the questions we like to answer. So you need some molecular dynamics. So we're going to have the MOF and the hydrogen inside all moving about. Hydrogen is very light. So you could do standard molecular dynamics, by which we mean Newton's laws, classical mechanics. Ideally, you'd like to solve the problem quantum mechanically for the hydrogen, because hydrogen is so light that you should actually describe it as a wavy thing instead of a point-like thing. That makes quantitative difference. And this is one of the things we wanted to accomplish in this project, but there were some difficulties. Okay, so this software is a modular software in some sense. So the quantum nuclear part is a driver module for the basic dynamics. Okay? This has been developed over many years. This is what the problem we ran into. So this quantum nuclear module is old. We've tested it many, many times and validated in serial, like our nightly build has a quantum nuclear test in it. It runs. We even have a small cluster at UIUC that's parallel. That's also done as part of the validation. Okay, so that was the status before we went on to blue waters. When you run it on this large MOF, which we cannot run locally, with many nodes and what's called beads, you have to replicate your system in the quantum simulation, it fails. What does it fail like? The typical failure is you have to run on 1,000 nodes for 3 hours before you get to the failure point. So it's very challenging to debug this problem. Okay? So we've spent about 9 months dealing with this. It's an irreducible, at the moment I would say it's irreducible because every run is slightly different than the next. That's a bad thing, but there we are. We've narrowed it down to a single module, but it's not been fully isolated yet. So I cannot present you results on this aspect of the physics. All right, is there a take-home message from our problem? Yes. How do you validate a parallel software when it's only possible to validate it on something as big as blue waters for thousands of nodes for at least 3 hours, right? No one has that sitting around in their backyard. This is what you can do locally these days. I don't have a solution to this problem. Will they give us an allocation just for our nightly build testing? Maybe we could ask for something like that. That's not very standard, though. But it is a problem. Okay, so what have we learned so far? So here's an example of a simulation. What we're talking about, the little gray things are H2 molecules. You see they come in pairs of hydrogen atoms. They're jiggling around. This is the corners which have the zinc in them. These are your organic connectors between the corners. And so we have lots of these movies. And they go on and on and on and on and on, and the hydrogen moves around. All right, here's one representation. So this is a 2D projection, okay? So the hydrogen started in this unit cell, and then we drew spaghettis tracking them around. So this is actually a small version of the MOF. It's 1/8 of the size, just for testing purposes. And so over the simulation, you can see they really do wander around. So it is diffusing. We're not just stuck somewhere jiggling. And when we run the full MOF, which is the real thing, this has 43 hydrogen molecules in it per unit cell, and so it looks the same. So we're well into the diffusive regime. Here's a different representation of the same data. So again, it's a 2D projection just to get a feeling. It's a heat map. So we figure out where all the hydrogens are and time average over the simulation, and then draw the probability as a color. And the yellow stuff is high and the blue stuff is low. So all right, so it seems to spend a fair amount of time in the void, that is detached and wandering around, but it also likes to spend some time in the corners. I have not analyzed this sufficiently to say anything more intelligent than that. Okay? The native binding sites are in the corners next to the zincs. So the fact that there's amplitude here, here, and here is not surprising to me. What I don't understand is like exactly why it looks like this at this temperature. This is at 77 Kelvin. Okay, those are some pictures for you. Diffusion, however, is a quantitative thing. So here's a standard equation for 3-dimensional diffusion out of a textbook, that if you know where your thing is at time 0 and you know where it is at time t, you subtract the vectorial position, square it, take the average over your ensemble, and look at it as a function of time. And for long times, it should be linear in t, and the coefficient is 6 times the diffusion constant. Okay? So here's literally what we do. This is the big MOF with 43 molecules. This is at 77 Kelvin. So I'm plotting you this thing versus elapsed time. It's a little more complicated because this is actually time elapsed. So like we're averaging over the simulation for the shorter times. Okay, this was a 36 picosecond long. Each little colored line is one of the hydrogen molecules. So some of them jiggle around a lot, some of them don't. And so the black thing is the time averaged. Sorry, the molecular averaged one. And every point has an error bar, but if I drew it, it'd be all black. So I just drew the error bars for you like at selected points to get a feeling that indeed here you have more uncertainty than you have there. Okay? And it's a particular curve because we know it goes through the origin and it should have straight line slope. So it's a 1-parameter fit for D. So you can do the, on the paper, you can do the statistical analysis and figure out that for this calculation, it was 8.5 plus or minus 0.5 times 10 to the minus 8 meters squared per second. That was a diffusion constant. People in the past have done simulations not with quantum mechanical models, but with force fields that they fit to some experiments and some regimes, and then they just ran them. So it seems like Depends how you want to look at this. Either we fit the force field or the force field fits us, but it's reasonable agreement. We've been able to extract diffusion constants at 2 temperatures for our 2 systems, just to get a feeling. So here's the diffusion constant for the first 2 rows. For a small version of the system, so this is more about testing it, and then the full thing at 2 different temperatures. These are all in this peculiar units here. All right, so you can see as the temperature goes up, yes, the diffusion goes up in both the smaller system and the larger system. The ratio of the 2 temperatures is similar, but it's not the same. And the diffusion coefficient is a bit lower in the bigger system than in the smaller system. I don't understand that at the moment, but it is statistically significant difference. Okay, so I don't understand why confining the thing to a smaller periodic cell does that, makes the diffusion faster somehow. Okay, so if we had run our nuclear dynamics, I would have told you about that too, and that would have been very interesting to see at the same temperature for the same size, how much does the diffusion coefficient change? But maybe we can do some of that in the last 3 months of the project. Okay, so we decided to use the remaining time that we were unable to use doing something different, because it's better to do some science than no science. So we decided that since we're developing, the same group of people on this PRAC is developing this GW calculation method, let's see how well we're doing there. So what is this GW thing? So we're doing electronic structure, right? We're explicitly describing the electrons, so we should be able to describe electronic properties. And we can describe electronic properties, but the method we're using, this density functional theory, the method I've been using up to now, is very good for bonds and the shapes of molecules and vibrations, but it's very bad for electronic excitation. So what does bad mean? So here's an old set of data. These are 3 systems, okay? These systems have an energy gap. That means you have to pay some energy to promote an electron to the next available state. Okay, here's the experimental gap in electron volt units. Here's this DFT prediction. I mean, the DFT prediction is like, it's positive and it's something, but it's off on the order of half to 1 electron volt. So is that a good thing or a bad thing? So you have to look at some real data. So here's the optical absorption spectrum. This quantity is proportional to that. For silicon, as computed by this LDA DFT method, that's the blue curve and the black curve. Okay? So they're different, but they kind of look the same. All right, so the way to figure out what precision you need is to look at the solar spectrum. Here's a solar spectrum. Photon energy, photon flux, and these are the ones that you can see. So it starts about 1.5 electron volt. All right, that's where it starts. So if you didn't know anything better and you had only the DFT calculation, because let's say you're designing a new material, right? Some new element or some new metal or something, and you're like, oh, this thing is great for solar absorption. See, it starts absorbing at 2 electron volts, right? And you'd be super excited because you can absorb all this stuff. But in fact, it starts at 3 electron volts, so it's pretty crappy. Okay? In fact, silicon is not a very good light absorber. We all know that. Indivisible. Okay? So errors of the order of half to 1 or 2 electron volts are very bad if you want to, say, design solar cells. Okay? So you need something better than that. And so this GW method delivers on that. Okay? The typical errors are now in the second digit, 0.1 electron volt or 0.2 electron volt. It's not perfect, but it gives you that. So then you're talking about something on this scale here. So you're happy enough designing materials with the GW method. So I won't show you a lot of equations, but I'll show you one equation. In the GW method, one of the important things you have to calculate is the response of electrons. So how much does the density of electrons change here at some place R when you change the potential of the electron field somewhere else? That's called the polarizability. So if your electrons are floppy, this is a big number. If electrons are not floppy, it's a small number. And you might say, why do you care about this quantity? It's because the GW method basically figures out the energy to excite electrons due to electron-electron interaction. So I'm an electron, and I'm going to get excited. I'm going to rearrange the other electrons around me. But we're charged, so we interact. So I have to know, when I rearrange myself and change the potential, how do the other guys rearrange themselves? So you need exactly this function. Here's the traditional way to calculate it in GW. There's a bunch of things here. You have to sum over all the states which have electrons, labeled by V, and all the states that don't have electrons. In principle, this is infinite sum, but you truncate somewhere. And you multiply all their wave functions together in this way and divide by the energy difference. Okay? So it has two indices R and R prime in your simulation cell. So this is a very large matrix. Okay? And it requires like quartic amounts of computation. You have two sum over the number of things in your system, plus in each one there's an R and R prime. So this is n to the fourth scaling. So the first thing we did is we wrote a parallel version using this Charm++ library, which scales very well. And we ran it on a big supercomputer. We ran it on the DOE Mira system. And we have to compare it to something. So we compared it to what's available publicly out there, very well-developed, high-quality Berkeley GW software. And so this is a system of 100 silicon atoms. And the axes are log-log scale, number of nodes, time to complete the calculation of P. So we can see this OpenAtom scales very well over orders of magnitudes of the number of nodes, and it's much faster than this one. But the point isn't that it's faster, the point that it continues scaling. So this is Grace. This is a thank you to the Charm++ parallel work runtime system. But the Mira system is actually relatively slow processors combined with relatively fast interconnects, all relative to each other. Okay? Blue Waters is a kind of a different regime. The processors are much faster than the interconnect if you were to compare it to Mira. So when we run the same calculations there, we see that this Berkeley GW is a lot better. It's much more compute heavy. And the costs, we were starting to run out of benefit here. So by being able to run 1,000 node jobs many, many, many times on Blue Waters, we were able to figure out which part of the calculation of this polarizability is expensive. So after 1 week of thinking and 1 week of coding, the graduate student at UIUC produced the orange curve. It's the same calculation, and it's just changing 40 lines of code once you figure out what's going on, because you need to run it this big. Otherwise, it's very hard to tell the difference up here, right? But here, you got an order of magnitude, basically, of difference. You can time it and figure out what's going on. And quick implementation change, and same thing's running about, 5-6 times faster. So we're feeling that this software is now good enough to be released, so we're going to release it this summer for public use. And that's thanks to having this resource available to be able to look at these things at large scale. So thank you very much for your time. This is just a summary of what I talked about.